Very good morning, dear students. Welcome to Tungal online classes. In today's class, let us discuss the electrostatics of conductors, that is, the behavior of the conductors in external electric field. Yes. The first property is that the electric field inside a conductor is zero. And to understand it, what we shall do is, let us consider a conductor which is placed in a uniform electric field. Yes, let us consider the uniform electric field of the electric field intensity capital E. Let a conductor be placed in this uniform electric field, and if the direction of electric field is along positive x-axis, this side we can consider a positive charge and this side we can consider a negative charge, which creates the electric field. Yes. So here what happens when the conductor is placed in this uniform electric field, we know that this conductor contains very large number of free electrons. Yes. So those free electrons, they all get drifted towards the positive side of the source. So when these electrons from the right side, they move towards the negative side here, that is to the left side. Here the equal number of positive charges are created. Okay. So here these positive and negative charges are created by the method of induction. Okay. Here we have the external electric field of intensity capital E, and because of these induced charges, these positive charges and these negative charges, there will be an electric field inside the conductor, which I can call it as a induced electric field. And this movement of the charges will continue until the magnitude of this induced electric field equals the magnitude of the external electric field. At the point of equilibrium, I can write the external electric field is equal to the induced electric field, and we can clearly see here the direction of the induced electric field is in the opposite direction of external electric field. So this cancels the effect of external electric field. Hence, inside the conductor, the net electric field will be equal to 0. Yes. So this is how we understand that the electric field inside a conductor is 0. The effect of external electric field gets cancelled by the induced electric field inside the conductor. The next point is that the electric charge inside the conductor is 0. To understand what we shall do is, let us consider a conductor here. Yes, and we have already stated that the net electric field inside the conductor, even if it is placed under external electric field, that is equal to 0. Okay. So for this we shall use the statement of the Gauss law. The Gauss law states that the integral of E into ds is equal to 1 divided by epsilon times of charge. Yes. So here the Q is the magnitude of the charge enclosed by the Gaussian surface. So since the electric field is equal to 0, so when I substitute the electric field intensity is equal to 0, I must consider the charge also equal to 0. So here inside the conductor, all over inside the conductor, we have the net electric field intensity equal to 0. Hence, there is no any charge enclosed by the Gaussian surface. We can state that the charge in the interior of the conductor is also equal to 0. Okay. So this is how we can state that the electric charge inside the conductor is equal to 0. Okay. The next important property is that the electric field on the surface of the conductor is perpendicular to the surface. Yes. So let us discuss this. Let me consider a conductor like this, which is placed in a uniform electric field. Let us place this conductor in a uniform electric field, then capital E is the magnitude of the external electric field. Okay. So let us first what we shall assume that the electric field, what happens if the electric field is not parallel to the, not perpendicular to the surface. Let us say I have some electric field along this direction. Okay. Let this electric field make an angle of theta with the surface of the conductor. So if it makes angle of theta with respect to the surface of the conductor, we can resolve that electric field into two components. One is perpendicular component, another is a tangential component. So here, this I can resolve it along tangential component and a perpendicular component. Let me call this as dP. Let me call this as ET. Okay, ET is the tangential component of the electric field. Okay, so when there is some magnitude of the electric field along the surface of the conductor, whatever charges on this surface of the conductor are there, that should produce something called surface current. Okay, so because of this electric field which is acting along the surface, tangential to the surface of the conductor, there must be surface current created. But when we see practically, when any conductor is placed in external electric field, there are only static charges. We do not observe any surface current. Okay, there is no flow of any electrical current on the surface of the conductor when the conductor is placed in electric field. Hence, we understand that there is no any surface component of the electric field. So to satisfy this condition, whatever electric current is there, that must be perpendicular to the surface of the conductor. However, maybe the surface at every point, the external electric field will be acting perpendicular to the surface of the conductor. This is how we can prove this statement. Yes. Next, we have fourth point. We can write it as the charge, the net charge of conductor. The charge of conductor resides on surface of the conductor. Here we can understand this using the theory of Gauss law. So here this is the Gaussian surface. This is the Gaussian surface. Since our electric field inside this conductor is equal to 0, since the electric field inside this conductor is equal to 0, and the charge, the electric field passing through this Gaussian surface is also equal to 0, that is true only if the charge inside this conductor is equal to 0. Okay, and whatever charge is possessed by the conductor, all that charge must be present on the surface of the conductor. We cannot have any charge within the conductor within the volume of the conductor. So all the charge possessed by the conductor will be present on the surface of the conductor. Yes. Next we have the electric potential. The electric potential is constant. Constant through the conductor. What is the meaning of this? See here. Let us consider a conductor which is placed in a uniform electric field of intensity capital E. Okay. So let us consider the left surface here. At the left surface, let the potential because of this electric field is V, and on the right surface let the potential is let me write this is V1 and this is V2 here. Okay, and inside the conductor we have already proved that the electric field intensity is equal to 0. Even though the conductor is present in the external electric field, there will not be any electric field within the conductor. So throughout inside this conductor, the electric field is equal to 0. Okay, and we have already proved that relation between the electric field and the electric potential, that is E is equal to magnitude of electric field intensity. I can write it as E is equal to dV divided by dr. Okay, dV is change in the potential, that I can write it as V2 minus of V1. Okay, so I can write it as V2 minus of V1. divided by dr is the thickness of this conductor I can consider. Okay, so that we write as dr itself. But since the electric field inside the conductor is equal to 0, I can write E is equal to 0. This implies that V2 minus V1 is also equal to 0. Okay, so when V2 minus V1 is equal to 0, the potential here, so I can write this is also equal to V, this is also equal to V, and inside the conductor there is no change in the potential dV. The change in the potential is equal to 0. So within the conductor also I can write the potential is the same. So throughout the volume of the conductor I can write the electric potential is equal to 0, because the electric field inside the conductor is equal to 0. Hence the change in the potential inside the conductor also is equal to 0. So throughout the conductor the electric potential due to the external field remains same. Yes. So this is how we can do this statement. Then we have 6th point, that is the charge density, the charge distribution on the surface of the conductor, conductor may not be uniform. So for this, let us consider a conductor of this shape. Okay. So even though I have the charge of Q here, yes, let us consider the surface is having some charge distributed uniformly like this. Right? See, if I consider this part of the conductor, the area is very, very small. If I consider this part of the conductor, the area is more here. So the surface charge density at this point, this is very large compared to the surface charge density here. Okay, here I can write sigma 1 is greater than sigma 2, because you know the surface charge density is equal to what? Q divided by area. At this point I have the minimum area, which makes sigma 1 much greater than sigma 2. At this point I have more area, so here I will have less value of surface charge density. So the surface charge, the distribution of the electric charge on the conductor may not be uniform. That I call it the charge distribution on the surface of the conductor may not be uniform. It depends on what is the shape of the conductor. Okay, if the shape is uniform, I will have uniform charge distribution. If the shape is non-uniform, definitely the charge distribution will not be uniform. Okay, so next we have important property called electrostatic shielding. How? Property of electrostatic shielding. So here, just here, let us consider a conductor which is placed in a uniform electric field again. Yes. And all over inside or within the inside of the conductor, we have the electric field is equal to 0. Okay. So just now we have proved that the net electric field inside the conductor is equal to 0, even though the conductor is placed inside a strong electric field. Okay. So this property can be used to safeguard some instruments which are under the influence of external electric field. Okay, to avoid that hazard, so that external strong electric field may affect the functioning of some important instruments or devices. So those devices can be saved by placing them inside the conductor. What we do here, let us consider I have some cavity. Okay, if I have some cavity inside the conductor, so throughout the inside of the conductor also I have the electric field is equal to 0. Hence within this cavity also we will have the electric field is equal to 0. Okay, I don't have any charge here, I don't have any electric field here. If we place any sensitive instrument within this cavity, so that can be protected by the strong electric field which is acting around that conductor. Okay, so this process of protecting the sensitive instruments within the cavities of the conductor where the electric field is equal to 0, so that is called as electrostatic shielding. Okay, so this is very important property of the conductor which makes to protect which helps us to protect the sensitive instruments from the strong electric field. Okay, so these are the behaviors or the properties of the conductor when they are under external electric field. Next, let us derive the expression for electric field at the surface of a charged conductor. For this, let us consider a conductor which is positively charged. We can also take negatively charged conductor. In this example, I am taking a positively charged conductor. Okay, and for this derivation, I have taken a cylindrical Gaussian surface like this. Okay, so this surface has three surfaces. This Gaussian surface has three faces here. This is first surface, this is second surface, and we also have the tangential surface of that cylinder. Okay, and because of this charge, we will have some electric field outside like this. Yes, and this electric field will be acting only through this surface. We will not have any electrical field through this surface because it is inside the conductor, and we know inside the conductor we do not have any electrical field, and we will not consider any electric field along the surface of that cylinder because both are parallel to each other, theta. So theta will be equal to 90 degrees there, hence we will not consider that tangential surface of the cylinder. Okay, and for this derivation, let us use the statement of the Gauss law, which states that the integral of E into ds is equal to Q divided by epsilon. Okay, so here I can take this electric field is constant, I can take it outside, so I write it as integral of ds, small areas. Okay, so that is equal to Q divided by epsilon naught, where Q is the charge present on the surface of the conductor and sigma is the surface charge density of the conductor. Okay, so here sigma is equal to Q divided by ds, where ds is the total area of the conductor. Okay, so when I integrate such small area, I can write it as E into, so here this ds I can write it as integral of ds is what, so that I can write it as ds into cos theta, where ds is the area of this small surface. So when I consider it as vector, I can write it as ds cos theta. Okay, so that is equal to Q divided by epsilon. Then, so here theta is equal to 0. What is this theta here? Theta is angle between the direction of the electric field and the surface vector. The surface vector of this surface. Always the surface vector will take it perpendicular to the plane of that surface. So in this condition, both these two vectors are parallel to each other. So theta becomes equal to 0. Here I am going to as E into integral of ds. So that is equal to Q divided by epsilon. So when I consider integral of all these such small surface areas, I can write it as E into ds. Okay, so E into ds is equal to, here I can write it as Q is equal to 1. From this I can write Q is equal to sigma into ds. So this is equal to sigma into ds I can write divided by epsilon naught. So these areas are equal, both get cancelled here. So I can write the electric field intensity as sigma divided by epsilon naught. This is the magnitude of the electric field intensity. When I write in the form of vector, I can write it as sigma divided by epsilon naught into n cap, where n cap is the unit vector along the direction of electric field. Okay, so this is the expression for electric field intensity at the surface of a charged conductor. So next we have the concept of polar and non-polar dielectrics. So before going to that, first let us understand what is the meaning of polar molecules and non-polar molecules. Okay, we know any atom is made up of, at the center we have nucleus, we will have certain number of protons, and around this nucleus we have electrons which are distributed in different orbits depending on their energies. Okay, so if I consider the net center of all these positive charges, that is protons, and so if I have some electrons like this, we will have one center of all those electrons, so that we consider it as the centers of positive and negative charges. Okay, in some molecules, the centers of the positive charges and all the negative charges, the net centers of the protons and the electrons, they will be coinciding with each other, but in some molecules they will not be coinciding. Okay, depending on this property, we can consider the molecules non-polar and polar molecules. Okay. In the non-polar molecules, what happens? Non-polar molecules. The centers of the positive and the negative charges of the constituent atoms, so that those will be coincident. For example, if I consider CO2 here, so this is my oxygen atom here, so this is the carbon atom, so this is again oxygen atom. All these centers are coincident with each other. Okay, so all those centers of the positive and negative charges are in line with each other. So this is CO2, this carbon dioxide is an example of a non-polar molecule. Okay, but when I consider the example of water, so water formula we have is H2O. So in this case, we will be having oxygen atom here. So we will have hydrogen atom somewhere here, and again another hydrogen atom will be somewhere here. Okay, if we measure the angle between this, so this angle comes out to be 105 degrees. So this is the oxygen atom. So this is the hydrogen atom. This is the hydrogen atom, and this is the oxygen atom here. Okay, so two hydrogen and one oxygen make out one H2O, that is one water molecule. When I consider the molecular structure of the water molecule, so all these three different atoms, they are not in the same line. These centers of the positive and negative charges, those do not coincide. Okay, so the molecules in which the positive and negative charges, the centers of positive and negative charges coincide. Such molecules we call them as non-polar molecules. Okay, so those are called non-polar molecules, and the molecules in which the centers of the net centers of the positive and the negative charges do not coincide, those are called as polar molecules, and the water molecule is the best example for polar molecules. And for non-polar molecules, we have the example of carbon dioxide, oxygen, hydrogen, and for polar molecules, we have the example of water molecule, we have the example of HCl. Okay, so this is the basic meaning of non-polar and polar molecules. Yes. And what happens when these non-polar and polar molecules are placed under external electric field? Okay, so first let us consider the case of non-polar molecules that we have. And as we know, we have in non-polar molecules all these positive and negative charges, they are aligned in line. So this will be something, this is the distribution of positive and negative charges. We have positive and negative charges like this. Okay, so this is when the external electric field is equal to 0. We do not have any electric field. Okay, so what happens when the same system of the molecules is placed under external electric field? So in that case, I can write E is not equal to 0. I have some magnitude of the external electric field. So how these molecules behave when they are placed in external electric field? So what happens? We know when electric field is something like this, we will have positive charge here and we will have negative charge here. So whatever positive charges are present in the molecule, all those positive charges are drifted towards the negative side of the source, and the electrons, the negative charges, they get drifted towards the positive side of the source. So electrons will move in the opposite direction of the electric field. Let us consider this is the direction of the electric field. We know the positive charges will move in the direction of the electric field, and the negative charges will move in the opposite direction of the electric field. So in the molecules there will be polarization. Okay, there is movement of these positive and negative charges in the direction of the electric field and in the opposite direction of the electric field respectively. The positive charges, they move in the direction of the electric field, and the negative charges, they move in the opposite direction of the electric field. Okay, so because of this, so we call the movement of these positive and negative charges in the direction of the electric field and in the opposite direction of electric field, we call it as a polarization. We call this process as a polarization. These charges are said to be polarized. Okay, and the extent of polarization depends on the nature of the molecules and the strength of the external electric field. Okay, so this is how the charges get polarized in case of non-polar molecules, and because of this polarization there is some induced dipole moment. Okay, so there is some induced dipole moment, and in case of non-polar molecules the induced dipole moment is significant. Okay, whatever the net dipole moment is created here, so that net dipole moment is mainly because of induced dipole moment. Okay, so this is how the polarization occurs in case of non-polar molecules when they are placed in external electric field. Okay, when I consider the polar molecules, the arrangement is not systematic like the polar or non-polar molecules. So here what happens? So here we have some random arrangement of the molecules here. It is something like this, right? So when the molecules are like this, so this is the distribution of the molecules when we don't have any external electric field. Okay, so when the same polar molecules, system of polar molecules is placed under external electric field, then E is not equal to 0. Means, so this is placed under external electric field. So first, whatever these molecules are there, those get aligned in the direction of external electric field. Let us consider the electric field is along positive x-axis. So this is positive charge, this is a negative charge. Because of that, I have electric field along positive x direction. So almost all these molecules, they get aligned in the direction of the external electric field. Okay, so this will be the alignment of external under the external electric field. Okay, so we can clearly see here almost all the positive charges are drifted towards along the direction of electric field, and negative charges are moving along the direction of opposite direction of electric field. Okay, so here whatever the net dipole moment is induced. Okay, so here the dipole moment induced, that is mainly because of alignment of these polar molecules. Okay, so because of that we have maximum dipole moment. There may be contribution of induced dipole moment also, but that is very less compared to the dipole moment produced because of alignment of these molecules, such that the positive charges are aligned in the direction of electric field, the negative charges are aligned in the opposite direction of electric field. Okay, in both cases of polar and non-polar molecules, the polarization it depends on what is the magnitude of the external electric field. Okay, so here we may get a question of 1 mark, that is what is the polarization. The polarization can be defined as it is the polarization is the dipole moment induced per unit volume of dye or the unit volume of the molecules. Right? So this is the meaning of polarization. It may be asked for 1 mark, and we know that the dipole moment induced, the polarization produced or the dipole moment induced is directly proportional. The dipole moment induced is directly proportional to strength of the external electric field. If the external electric field is strong, the polarization produced will be more. Hence, the dipole moment induced will also be more. I can write as E is equal to psi into E. Okay. So this psi we call it as electric susceptibility. So this constant we call it as electric susceptibility. They can ask 1 mark question that what is electric susceptibility. So this can be written as P divided by capital E. Is the dipole moment produced per unit electric field. Okay, so the dipole moment produced per unit magnitude of the external electric field. So this is nothing but electric susceptibility. Let us understand the basic meaning of dielectric. Dielectric material, it is a simply non-conducting material in which the opposite charges are developed on its two surfaces when that material is placed in external electric field. See here, let us consider an external electric field. Okay, let me consider some dielectric medium like this. Okay, so when the dielectric medium is placed inside external electric field, so let us consider the electric field is along positive x-axis, so that we will have some positive charge here, we will have negative charge here which is producing that electric field. In this condition, the negative charges are induced on the left surface towards the positive charge of the source, and the positive charges are induced on the right surface of that medium towards a negative charge of the source. In conductor also similarly the charges are induced, but in conductor what happens, the induced electric field will be equal to the external electric field, both will be equal and opposite to each other. But in dielectric medium, whatever the magnitude of the induced electric field is there, that magnitude will not be equal to the external electric field, that will be somewhat less than the magnitude of the external electric field. Okay, such non-conducting material in which the opposite charges are developed on the two surfaces of the material when that material is placed in external electric field is called a dielectric. Yes, water, air is an example of air or vacuum is a dielectric medium. Transformer oil is another example of a dielectric medium. Okay. Then we have a constant called dielectric constant. See here, whenever I have air medium, air or vacuum medium which is under external electric field. Okay, so if I have some external electric field and I have the medium as air, in air medium, if the electric field intensity induced is E naught. Let us consider the electric field intensity induced in the air medium or vacuum medium because of external electric field, if it is E naught. Okay, when the same air or vacuum medium is replaced by some other dielectric medium like glass or transformer oil, let us consider if I have some other medium. Okay, if I have some other medium other than air or vacuum, the electric field intensity induced, let it be capital E. Okay, I am using same electric field, the strength of the electric field is not changing, but the intensity produced because of the difference in the medium, let it be capital E here. And it can also be proved that always the electric field intensity induced in the air medium is maximum compared to the electrical field intensity produced in some other medium. Okay, dielectric constant is the ratio of the electric field intensity produced in air medium and the electric field intensity produced in some other medium than air. This I can write it as K is equal to E naught divided by E. Okay, so this is the dielectric constant. Yes, and we can also prove that the electric field intensity will be reduced when the air is replaced by any other dielectric medium. Next we have important concept of electrical capacitance. See here, we have seen different methods of charging. Okay, let me consider a conductor. In its stable condition, the number of electrons of that conductor will be equal to the number of protons in the conductor, so that the net charge of the conductor will be equal to 0. But I have so many different methods by which I can charge this conductor. Okay, I can give extra charge to the conductor. Okay, either I can make it positively charged or I can make it negatively charged. So let us consider I am making it positively charged. Okay, and there is some limit for that charge. Okay, it cannot store any number of charges. There is some limit for the storage of the charge. Yes, the maximum charge that can be stored by the conductor, let it be equal to Q. Yes, and when, see here, when the charge of the conductor is equal to 0, that is when this conductor does not have any excess charge, in that condition we know the electric potential is also equal to 0, because we have the formula for electric potential is equal to what? V is equal to 1 by 4 pi epsilon naught Q divided by R. At any point P here, the electric potential because of this source charge, that is conductor, will be equal to 0, because it does not have any extra charge. The net charge of the conductor is equal to 0. But when we give the extra charge to that conductor, because of the extra charge at any point P, there will be some electric potential given by 1 by 4 pi epsilon naught Q divided by R. Okay, at any point P, where P is the distance of that point from surface of the conductor. Okay, here since charge is not equal to 0, it gained some electric potential. Okay, so whenever any conductor gets charged, its potential increases from 0 to V. When the conductor does not have any net charge, the potential is equal to 0, but as we charge that conductor, its potential goes on rising. Okay, so this potential is directly proportional to charge present on the conductor. Okay, so this we can write it as Q is directly proportional to the potential. Q is directly proportional to V. We can write it as Q is equal to C into V. Okay, so here C we can write it as C is equal to Q divided by V. This is this term C we call it as electrical capacitance. Okay, so in general meaning, it is the capacity of any conductor to store the charges. If the capacity of the conductor is more, it means that it can store more number of charges. Okay, this property of the conductor we call it as electrical capacitance. In mathematical term, we can write it as C is equal to Q divided by V. So this we can state as it is the amount of charge to be given. It is the amount of charge to be given to the conductor to rise its electric potential by 1 volt. It is the charge per unit potential, or it is the amount of charge to be given to the conductor to rise, to increase its electric potential by 1 volt. Always there need not be potential equal to 0. We may have some initial potential. Okay, if we want to rise its potential by 1 volt again, we have to give extra charge to that conductor. Okay, the extra charge that we are giving to the conductor to increase its electric potential by 1 volt is called electrical capacitance. And the SI unit of the capacitance is, so we have the expression for capacitance, Q is equal to what? C into V. I can write C is equal to Q divided by V. And the definition of capacitance, we have defined it as it is the amount of charge to be given to the conductor to rise its potential by 1 volt. Okay, so in this equation, let us consider if Q is equal to 1 coulomb and V is equal to 1 volt, automatically C will be equal to what? 1 unit, and the unit of capacitance is farad. Okay, so we are using the unit of farad. This can also be written as 1 farad like this. Okay, the capacitance of any material is said to be 1 farad if 1 coulomb charge given to that conductor rises its potential by 1 volt. Okay, so this is the mathematical definition of 1 farad capacitance. The capacitance of any conductor is said to be 1 farad if 1 coulomb charge given to that conductor rises its electric potential by 1 volt. Okay, so this question is asked for 1 mark. Yes. Next we have capacitor. Capacitor is the device which is used to store the charges. Capacitance is property of the conductor. Capacitor is the device which is used to store the electric charges. Okay, and for our syllabus we have the parallel plate capacitor, and the symbol of parallel plate capacitor is like this. Okay, so this is the pictorial representation of a parallel plate capacitor. Here the capacitance of the capacitor is constant if the capacitance is variable, and that is represented by this figure here. So these are the pictorial representations of the constant value capacitance capacitor, and here it is the capacitor of a variable capacitance. Okay, this can be asked for 1 mark. Okay. Then let us discuss the principle of a parallel plate capacitor. Okay. Principle of a parallel plate capacitor. See here, let me consider a capacitor of this shape. Let me have some rectangular conducting plate like this, and I can charge this conductor. Okay, if I have only one plate like this, the maximum charge I can store, let it be Q. Okay, there is some limit to store the charge on this conductor, but somehow we can make some arrangement so that I can store more than this charge of Q. Okay, and how that is done, so that we shall understand in this principle of parallel plate capacitor. Yes, let me consider a parallel plate. I am showing only one surface. This is actually parallel plate. Here I am showing only one edge of that conductor. So here it is the edge of a conducting plate. Okay, very thin conducting plate. Let us consider I have stored some maximum charge on this. Let us make this positively charged here. Yes, so I have stored maximum charge possible on this conductor. So when I have only one conductor here, I can store some charge of Q. Okay, now what we shall do, let me bring another similar identical metallic conductor here of the same shape and size. I am bringing another identical metallic conductor. When this metallic conductor is placed very close to the first surface, let us consider this is a first plate, and let me consider another metallic plate too, which is brought very close to the first plate. Okay, so we know the method of induction. Because of induction, what happens on the left surface of this second plate? On the left surface of this second plate, we have negative charges induced. Okay, we have the negative charges induced, and because of these negative charges on the right surface, we will have equal number of positive charges. Okay, there will be charging of metal plate 2 because of the method of induction. Okay, here now initially let us consider, because of this charge Q, let us say there is some electric potential developed on the conductor. Okay, let that potential developed is V. Okay, so because of this charge, in the absence of second plate, let the electric potential developed on the first metallic plate, let it be V. Okay, now what happens when we have second plate placed close to this? So here there are some negative charges. Okay, these negative charges nullify the effect of equal number of positive charges here. Okay, what happens here? These negative charges induced which are close to this metal plate, they will nullify the effect of positive charges, or they will try to reduce the potential here. Are you getting it? Because of these negative charges, the potential of this first plate will reduce. These positive charges may increase the potential, but these negative charges are very close to the first plate. Hence, the effect of these negative charges on the left surface is more than effect of the positive charges. Okay. Hence, here the potential of the first plate reduces because of these negative charges. Okay. Again, to still reduce the potential of this. So, why we are reducing the potential of a first plate? Because whenever I charge this conductor, whenever I charge this metal plate, there is some potential developed. There is some maximum value of that potential limit. Okay. So, again if I reduce the potential, I can store still more number of charges by reducing the electric potential. Okay. So, now again what I will do, I will connect this right surface of the second plate. I will connect this right surface of the second plate to earth. We know earth can accept any number of electrons, and it can also donate any number of electrons. Okay, so what happens here? These positive charges are neutralized by the electrons donated by the earth. Okay, whatever number of positive charges are there, all those positive charges are neutralized by the earthing method here. So when these positive charges are neutralized on the second plate, we have only negative charges, which reduces the potential of the first plate. So this is how the potential of the first plate is still reduced. Hence we can store more number of charges here. Q, when I have only one plate, the charge I could store was only Q. When I introduce another identical plate very close to the first plate, I can store more charge, which is Q dash. Definitely Q dash is more than Q. Now let us derive the expression for capacitance of a parallel plate capacitor, which regularly arrives for 3 marks. Yes, let us consider two identical parallel plates P and Q. Let P is positively charged and Q is given a negative charge, and the surface charge density on plate P is a plus sigma and that on Q is a minus of sigma. And because of these two opposite charges, let there be electric field induced between the parallel plates. Okay, and we know this electric field intensity is given by sigma divided by epsilon naught. Okay, where sigma is the charge density on both the plates. So let this be equation number 1. This is the electric field intensity between the parallel plates. And we know the relation between electric field and electric potential. The magnitude of that electric field is given by what? E is equal to dV divided by dr. Okay, dV is the potential difference, dr is the distance between both the points here. So here this distance is nothing but d. We are taking both the plates separated by distance of d. So dr can be replaced by d here, and dV, that is the potential difference, let us take it as V. Okay, so this I can write it as E is equal to V divided by D. Okay, so this potential I can write it as V is equal to E into D. Okay, then so here I can write this E as a sigma divided by epsilon naught. I can write it as V is equal to sigma divided by epsilon naught into D here. And we know by the definition of surface charge density, sigma is equal to what? Sigma is equal to Q divided by A, where A is the surface area of the parallel plates here. Okay, the area of the rectangular plates, that we can take it as so this is surface area. This surface area we can take it as capital A. So I can replace this sigma by Q divided by A. I can write electric potential is equal to what? Sigma is nothing but Q divided by A. Here I will have Q D divided by epsilon naught. Okay, let this be equation number 2. Then by the basic definition of capacitance is defined as Q divided by V. In this expression, replace this V by equation number 2. I can write C is equal to Q divided by Q into D whole divided by A into epsilon naught. Okay, so I can write C is equal to, so these two get cancelled here, A into epsilon naught divided by D. Okay, this is the expression for capacitance of a parallel plate capacitor. Okay, here A, it is the area of the capacitor plate, epsilon naught is permittivity of the free space, assuming that capacitor is placed in a air medium, and D is the distance between the plates of the capacitor. Okay, many times they may ask the question on what are the factors affecting capacitance of parallel plate capacitor. So for that, you just remember this equation. These are the factors which affect the capacitance of a parallel plate capacitor. Okay, that is the area of the capacitor plates, the medium, the permittivity of the medium, and the distance between the plates. Next, let us derive the expression for capacitance of parallel plate capacitor when a dielectric slab is placed between the plates of the capacitor. Okay, so for this, let us consider the parallel plate capacitor with plate P, which is positively charged, and plate Q, which is negatively charged. And let Q is the magnitude of the charge on each plate, and sigma is surface charge density of the plates here, and let d is the distance between the plates of the capacitor, and let us have a dielectric medium or dielectric slab of thickness T in between these capacitors plates. Okay. And because of the charges on plates P and Q, we have some electric field intensity, that is E naught. Let E naught is the electric field intensity between the plates P and Q. Okay. And we know on the dielectric slab there are opposite charges developed or opposite charges induced on both the surfaces here. On the surface near positive plate here, we have negative charges induced. On the surface which is close to plate Q, we have positive charges induced because of polarization. Okay. And because of this polarization or these positive and negative charges, there will be another electric field induced in the dielectric slab. That induced electric field I call it as a EP. Okay. So, this EP is developed because of polarization of the charges in the dielectric slab. Okay. Now, see here, let us consider the net electric field, the net or the reduced electric field, in dielectric slab, that will be equal to what? E naught minus of EP. Okay. So, that will be E naught minus of EP, and this E naught minus EP I can call it as a capital E. Okay. So, this reduced electric field intensity will be acting for the length of T, that is the thickness of the dielectric slab. And if there is any gap between dielectric slab and these parallel plates, so that gap is given by what? D minus of T. Okay. In that gap, the electric field intensity acting will be equal to what? E naught. Okay. E naught is the electric field intensity acting in the gap between dielectric slab and the parallel plates of the capacitor. Okay. So, there are two electric fields here, one is E naught and another is a capital E, that is equal to what? E naught minus of EP. Because of these two electric fields, we will have some electric potential. Okay. So, that electric potential between the plates, between plates of the capacitor, is given by, that I can write it as V is equal to that is capital E into T, because this reduced or net electric field intensity is acting for the length of T plus of there is electric field intensity E naught. It is acting between electric plates and the dielectric slab here. So, that I can write it as E naught into that gap is given by what? D minus of T. Okay. And how did we get this relation here? So, that we got it from, I have the relation E is equal to dV divided by dr. Okay. dV is a potential difference, dr is the distance. Okay. Or this I can write it as V divided by R. So, I can write V is equal to E into R. Using this relation, I am writing the expression for electric potential. Okay. E is the magnitude of electric field intensity, T is the length or thickness here. Okay. So, now we have another relation that, so when I have electric field intensity of E naught between the plates of the capacitor, that electric field intensity can also be written as E naught is equal to what? Sigma divided by epsilon naught, where sigma is the surface charge density present on the plates of the capacitor. Okay. So, here I am using E naught as a sigma divided by epsilon naught. I can write the same expression as V is equal to capital E into T plus of E naught. I can write it as sigma divided by epsilon naught into D minus of T. Next, this equation I can simplify as, see here, we have another relation that dielectric constant is given by E naught divided by E. It is the ratio of electric field intensity in air medium and electric field intensity in some other medium other than air. So by using that I can write it as V is equal to, so from this I can write E is equal to what? E naught divided by K. Okay. So here I can write V is equal to, E is nothing but E naught divided by K into T plus of E naught into D minus of T. I am just replacing E by E naught divided by K by the definition of dielectric constant. Okay. Then we also have another relation, that is, in this case, when I have the surface charge density of sigma, this electric field intensity can be written as E naught is equal to what? E naught is equal to sigma divided by epsilon naught. Okay. That is the electric field intensity produced between plates of the capacitor. By using that relation, I can write in this case V is equal to E naught, I can write it as a sigma divided by epsilon naught into K into T plus of sigma divided by epsilon naught into D minus of T. Okay. So here sigma divided by epsilon naught is constant, I can take it outside. V is equal to sigma divided by epsilon naught, here I write inside bracket T divided by K plus of D minus of T, right. So I can write it like this. Again we know the surface charge density sigma is given by what? Sigma is equal to Q divided by A. So let us replace this sigma, that is surface charge density, by Q divided by A into epsilon naught, inside bracket we shall write T divided by K plus of D minus of T. Okay. This is the expression for electric potential between plates of the capacitor. Okay. Now we have the definition of capacitance, that is given by capacitance of the capacitor is given by what? C is equal to Q divided by V. Okay. Now replace this V by this expression, I can write it as Q divided by, here I will have Q by A into epsilon naught, inside bracket I have T divided by K plus of D minus of T. Okay. So this 2Q gets cancelled here, again I have capacitance given by C is equal to epsilon naught A divided by T divided by K plus of D minus of T. Okay. Then let us take this D outside here, I can write it as C is equal to epsilon naught A divided by D, I will take it outside, so that I will have T divided by D into K plus of 1 minus of T divided by D here. I am taking D outside of this bracket, so here I will have T divided by D into K plus of 1 minus of T by D. Okay. Then when we did not have any dielectric slab, in that condition the capacitance was given by, let us call that as C naught. C naught is equal to epsilon naught A divided by D. Okay. So let this be equation number 1, let this be equation number 2. Let us divide equation number 2 by 1, so that we can get it as C naught divided by C is equal to what? Epsilon naught A divided by D whole divided by, here also we have epsilon naught A whole divided by D inside bracket T by dk plus of 1 minus of T by D. Okay. This epsilon naught A divided by D and this epsilon naught A divided by D get cancelled here. So this C naught divided by C will be equal to what? This goes to the numerator. We will have T divided by dk plus of 1 minus of T by D. This expression I can simplify as C is equal to what? C naught divided by T divided by dk plus 1 minus of T by D. This I can write it as C is equal to C naught divided by 1 minus of T by D inside bracket I will get 1 minus of 1 by K. This denominator is less than 1, hence always C will be greater than C naught. Okay. So this is the expression for the capacitance of the capacitor when a dielectric slab is placed in between the plates of the capacitor. Okay. Hence, by using the dielectric slab, we can increase the capacitance of that capacitor. Yes.